So far, we've used known values of either concentrations of reactants and products or pressures of reactants and products to find equilibrium constant values, either K sub C or K sub P. Now, we're going to look at a situation where we know the equilibrium constant value K sub C and want to try and find what the equilibrium concentrations are for the reactants and products. So our sample calculation D begins with the reaction of 2 hydrogen iodide gas yields hydrogen gas and iodine gas. And so the problem, 5 moles of HI is introduced into an evacuated 4-liter flask. Again, the word evacuated means that there is no other gas present, no other substance present. It's a vacuum until the hydrogen iodide is introduced. This is allowed to come to equilibrium at a fixed temperature. If K sub C at this temperature is 54, what are the concentrations of the reactants and products at equilibrium? And just a short note here that the importance of converting to moles per liter of the known reactants and products cannot be stressed enough, because again, K sub C, we're relating molar concentrations in our equilibrium expression. As noted before, we want to find the molarity of each of the reactants and products, again moles per liter. So we're going to take our number of moles of hydrogen iodide and divide it by the 4-liter volume, and that will give us 1.25 moles per liter of hydrogen iodide. Once we know what our beginning concentration is of our reactant, we can then set up what's called an ice chart. And an ice chart is a way that we'll keep track of changing concentrations in an equilibrium system. The I represents initial concentrations, the C represents the change in concentration, and E represents the concentration of the reactants and products at equilibrium. As we answer sample calculation D, let's take a look at the ice chart. Our initial concentration of the hydrogen iodide is 1.25 moles per liter. The concentrations of our hydrogen and our iodine are 0 moles per liter each. Now when we go to change, the stoichiometric coefficients for each of the reactants and products becomes very important. For instance, for every increase in hydrogen and iodine by an amount x, the hydrogen iodide will change by minus 2x. And would you correct this as you work through this at home? Where it says change, I have minus 2 under the hydrogen iodide. That should be minus 2x, and you can see on the E line here I do have 1.25 minus 2x as the equilibrium concentration, but I inadvertently left that out. For that I apologize. But we would have our initial concentrations of 1.25 mole per liter for hydrogen iodide, 0 moles per liter for hydrogen and iodine. The change for hydrogen iodide will be minus 2 times x. The change for hydrogen and iodine will be plus x for each respectively. At equilibrium, the final concentration of hydrogen iodide will be 1.25 moles per liter minus 2 times x. The concentrations of hydrogen and iodine will be x for each respectively. So once we've filled out our ice chart, we're then going to write the equilibrium constant expression and substitute the values of E from the ice chart into that equilibrium constant expression so that we can then solve for the value of x. Let's take a look at our equilibrium constant setup. My K sub C, or equilibrium constant for this, is 54. So I'm going to put 54 is equal to the concentrations of H2 times the concentration of I2 divided by the square of the concentration of hydrogen iodide on the bottom of this expression. When I substitute in the values from the ice chart, I have x times x on top divided by 1.25 minus 2x, that entire quantity squared. Now it's very important that you remember that when there's a coefficient greater than 1, that has to be reflected from the balance equation, that has to be reflected in the equilibrium constant expression as a power for whatever concentration and reagent or reactant or product that is related to. So we simplify this a little bit further by putting 54 is equal to x squared divided by 1.25 minus 2x squared. Now, I could have written the bottom as 1.25 minus 2x times the quantity of 1.25 minus 2x, but I left this written as its square just for simplification. I can simplify this further because we have a situation where when I have x squared divided by 1.25 minus 2x, that quantity squared, it sets up a situation that is known as a perfect square. And one of the ways that I can simplify this is to take the square root of everything in this expression. So I'm going to take the square root of 54 is equal to x, which is the square root of x squared, divided by 1.25 minus 2x, which is the square root of 1.25 minus 2x, that quantity squared. When I do that, the square root of 54 is 7.3 is equal to x divided by 1.25 minus 2x. So when you're confronted with a situation where you have this perfect square, it can help you simplify things, and you can actually solve for x without having to resort to the use of a quadratic equation. And if we can avoid using a quadratic, it's to our benefit that we do, just in terms of time. Now that I've simplified my equilibrium constant expression by taking the square root of each quantity involved, I can go ahead and use algebra to rearrange the expression, combine like terms, and solve for x. So my 7.3 being equal to x divided by 1.25 minus 2x, I can multiply both sides of this equation by 1.25 minus 2x, which drops it out of the right side of the equation and leaves us on the left side with 7.3 times the quantity of 1.25 minus 2x is equal to x. When I multiply through on the left side, I get 9.1 minus 14.6x is equal to x, and then I can add negative 14.6, actually, excuse me, I can add 14.6x to both sides to combine my like terms. So I'll have 9.1 is equal to x plus 14.6x, which means that the 9.1 is equal to 15.6x. I can simplify this further algebraically by dividing both sides by 15.6, which will cancel it on the right-hand side and allow me to isolate x and solve for it. So 9.1 divided by 15.6 will give me the value for x, which is 0.58 moles per liter. Please understand that when you are solving for x in an equilibrium constant expression that involves concentrations, the unit for x will be moles per liter, here represented by a capital M. Once I've found my value for x, which is the change in concentrations for the reactants and products, I go back to my original ice chart and I substitute those into the change line. So my initial concentrations again were 1.25 moles per liter for the HI and 0 moles per liter for each of the H2 and the I2. The change now will be for the HI minus 2x, which is minus 2 times 0.858 moles per liter. For hydrogen and iodine, respectively, the change is plus x, or plus 0.58 moles per liter. At equilibrium then, I take my equilibrium concentration for HI is 1.25 moles per liter minus 2 times 0.58 moles per liter, which leaves me with an equilibrium concentration of 0.083 moles per liter. The concentrations for hydrogen and iodine are the same. Both are plus the x value, so 0 plus 0.58 moles per liter gives us an equilibrium concentration for hydrogen and iodine of 0.58 moles per liter for each of those. So final concentrations of the reactant and products are concentration of HI is 0.083 moles per liter, H2 is 0.58 moles per liter, and I2 is 0.58 moles per liter.